So now we are going to look at 4 questions that are related to chapter 8. So molecule C8H10F2 has no triple bonds. It has one ring. How many double bonds it has? So a double bond consists of a sigma and a pi bond. And rings and pi bonds are unsaturations. Saturated molecule satisfies formula of CnH2n+2. Each unsaturation means that molecule has 2 fewer hydrogens. And so, in general, for ordinary organic compounds, where this formula applies to, that means that unsaturations are rings, double and triple bonds. Each ring is one unsaturation. Each double bond is also one unsaturation because it has one pi bond. And each triple bond constitutes 2 unsaturations because triple bond has 2 pi bonds. So rings and pi bonds are unsaturations. And if you add them up, that tells you how many hydrogens are basically missing from a molecule compared to saturated open chain compound. So to figure out how many double bonds are in this compound that has no triple bonds but has one ring, we have to calculate degree of unsaturation. And the formula for calculating degree of unsaturation is 2n plus 2 minus m divided by 2. N is number of carbon atoms, and m is total sum of hydrogens and halogens. And don't forget halogens. So C8H10F2. 2 times 8 carbons plus 2, that's 18, minus 12, that's 10 hydrogens plus 2 fluorines. Halogens, don't forget halogens. A lot of students would make mistake here and would put 18 minus 10 and end up with wrong answer. It's 18 minus 12. 10 hydrogens and 2 halogens. Divided by 2, that's 6 divided by 2, 3 unsaturations. So there are 3 unsaturations, so total of number of rings and pi bonds is 3. There is one ring, that means there are 2 pi bonds. 2 pi bonds could be a triple bond or 2 double bonds. Well, you already know that there are no triple bonds. It says so right here. So that means there are 2 double bonds. It's relatively simple formula, relatively simple calculation. The only trick here is don't forget to include halogens. Students forget that all the time. Okay, next one is nomenclature. So let me see if there are any questions about this one. Okay, I don't see any questions. Of course, you can always ask questions at the end. Question number 9. What is UPAC name of the following compound? Lots of double bonds, so it may look a little bit scary. But you need to know double bond as a substituent. And there are 2 substituents involving double bond that you need to know. Vinyl, which is just double bond itself, so CH-CH2, that's vinyl, and allyl, double bond separated from rest of the molecule by CH2 group. It will be CH2 and then double bond. So obviously this is vinyl substituent. So that's first thing that you need to know, how to name the substituent on the ring. Now, how about ring itself? Well, ring is obviously cyclopentane ring. There are 2 double bonds. Each double bond makes it an alkene. So 2 double bonds, alkene is -ine, has suffix -ine. 2 double bonds is diene. 3 double bonds will be triene, 4 tetraene, and so on. So 2 double bond is diene. So cyclopentane with 2 double bonds is cyclopentadiene. You ignore the substituent. You give smallest possible numbers to carbons of the double bonds. And so they would be 1 through 4. A double bond must have consecutive numbers, 1, 2, 3, 4. You cannot start here where we have carbon 2. You cannot start 1 there. Because if this was 1, then 2, 3, 4, 5, then you would have 1, 5 for double bond. You cannot have that. They must be consecutive numbers. So this is the numbering. And then on carbon 2, vinyl group is bonded to that carbon. So it's 2 vinyl, 1, 3 cyclopentadiene. A lot of students would make mistake here and name it one vinyl, assuming that you give the smallest possible number to substituent. But no, if you have two double bonds, then you have to name or number those 4 carbons of the two double bonds with smallest possible set of numbers, and then whatever this substituent gets. And obviously, numbering 4 as 1 and 3 as 2, 1, 2, 3, 4, that would give 3 to vinyl group, so that's obviously not correct, because once you numbered, there are always 2 ways in a ring to number double bonds or substituents, clockwise and counterclockwise. And so you should test both to see which one gives smaller a number to substituent. So that's where substituent comes in, to decide whether to number them clockwise or counterclockwise. Okay. Any questions about this one? I don't see anything. Again, you can ask questions at the end. Question number 10. What is the order of priorities of the following substituents according to Kahn-Ingold-Prelog rules? So first 2 examples, there are 3 examples, 3 different ones, and you're supposed to provide order of priorities. First 2 are something we covered in chapter 8, where you are determining whether double bond is E or Z, as opposed to cis-trans nomenclature. EZ is systematic UPAC nomenclature. So for each of the carbons of the double bond, when substituents are different, you should determine priorities, which one has priority 1 and priority 2. And same, so this 2 could have been part of one double bond. Let's deal, so for each carbon of the double bond, you determine which one is substituent 1, which one is 2. And you are looking at atom directly bonded to the carbon of the double bond. So which atom has higher atomic number? Not higher atomic mass, but higher atomic number. And so that's shown here, the same ones. We have carbon versus carbon. That's a tie. Obviously, 2 carbons have atomic number of 6. Then you look, for each carbon, you have 3 other substituents. Which of those 3 has the highest priority, highest atomic number? Here, on the top carbon, it's chlorine. On the bottom, it's fluorine. So now you compare those 2. Which of them has higher priority, higher atomic number? And it's chlorine. So that gives the entire substituent higher priority. So this is substituent priority 1, substituent priority 2. So if you have substituents on carbon atom where you have a tie, you have atoms of the same atomic number, you keep going down the path of that substituent of the highest priority until you find a difference. And then atom with higher atomic number has priority. Second one is a little bit more complex because you have to convert multiple bonds to single bonds involving, and you do that by adding virtual bonds and virtual atoms. So bottom substituent doesn't have any multiple bonds, but top one has carbon-oxygen double bond. So it's a good idea to be able to follow the path of highest priority to draw a complete structural formula. And then for the top one, you redraw the substituent, but instead of carbon-oxygen double bond, you draw carbon-oxygen single bond. And then for carbon atom, it used to have double bond. You draw another single bond, that's virtual bond. And so what is at the other end of that bond for this carbon? It's oxygen. So virtual atom is oxygen. For oxygen, you have to convert each double bond to 2 single bonds. So what is at the other end of the bond to oxygen? It's carbon. So you put carbon here. So you see carbon-oxygen double bond became 2 carbon-oxygen single bonds. And from oxygen's point of view, oxygen-carbon double bond became 2 oxygen-carbon single bonds. Virtual bonds and virtual atoms are shown in blue. And there is nothing bonded to virtual bonds or virtual atoms, or nothing bonded to virtual atoms. So that's where the chain stops. If you're comparing priorities, that's where the chain stops. And now we are comparing them with respect to this carbon of the double bond. So we have 2 carbons, that's the same priority. Then what is the highest priority? Here it's oxygen. Here we have two oxygens. But the top part, carbon, oxygen, carbon, is higher priority than carbon, oxygen, nothing. Because carbon, even though it's virtual, has higher priority than nothing. Atom always has higher priority than nothing. So this is the path of highest priority. So it's carbon versus carbon, oxygen versus oxygen, carbon versus carbon. It's a tie. But then here we have hydrogens of this carbon. This is not virtual atom. We have three hydrogens. Hydrogens versus nothing. Hydrogens have higher priority. That's the only time when hydrogen atom has higher priority, because hydrogen atom has the lowest possible atomic number, 1. So in this case, that's the only time when hydrogen atom has higher priority, hydrogen versus nothing. And so bottom substituent has higher priority, top lower. And in the last example, we have tetrahedrally substitute carbon. That's something you will encounter a lot in chapter 11. So that will be test 3, but it's not a bad idea to give you an example, simple one. So in this case, for this, with respect to this carbon, we need to list these 4 substituents, but since they're all bonded to one carbon, now we are listing them in order of 1 to 4. Highest atomic number is the highest priority, that's bromine, priority 1. Then second highest is carbon, 2. Now we have two hydrogens, deuterium and protium. Protium is always indicated as H, deuterium as D, and tritium as T. Deuterium is, so when we have two isotopes of the same element, then obviously they must have same atomic number. It's the same element. So only then we use higher mass. So higher atomic mass has higher priority. So when there are two isotopes of the same element bonded to carbon, then higher priority is given to isotope of higher mass. So deuterium has priority 3 and protium 4. So that's it. Okay. Any questions about this one? See first if nothing typed up. Any questions? Okay. And let's look at chapter 11. What is UPAC name of the following compound and how many isomers of it are possible? So there are 6 carbons, and you can see we have methoxy substituent on 1 carbon. That means that that's going to be carbon 1, because when we name, this is obviously a diene. We have 2 double bonds, and you have just seen we number diene, carbon atoms of a diene in such a way that we assign carbons of double bond smallest possible set of numbers. So numbering from left to right, right to left will be same set of numbers, 2, 3, and 4, 5 for double bonds. But here on the right carbon, at the right end, we have methoxy substituent. So that's going to be carbon 1. So this is 6 carbons, it will be hexane. With 2 double bonds, it's hexadiene. Double bonds are between carbons 2 and 3 and 4 and 5. Of course, we use only smaller numbers to indicate position of double bond, because if we say 2, that means between 2 and 3, and 4 between 4 and 5. So it's 2,4-hexadiene. And on carbon 1, we have methoxy group. I hope you know how to name this from naming of ethers. Methyl oxy, or in general alkyl group, whatever alkyl group here is, alkyl oxy, alkoxy, methyl oxy, methoxy. So 1 methoxy, 2,4-hexadiene. How many isomers are possible? You're looking for symmetry. So if both double bonds can be E or Z or cis strands, then there are up to 4 possible substituents. Maximum number of substituents is 2 to the power of n, where n is number of double bonds. And so there are 2 double bonds, so 2 to the power of 2, 4. But that's maximum number. There could be fewer. If one double bond does not exhibit cis strands or EZ isomerism, then there are only isomers due to the other double bond, only 2, E or Z. And if both double bonds exhibit EZ isomerism, but molecule is symmetrical, let's say both of these groups were methoxy, 1 and 6 methoxy, or both were methyl, 1 and 6 were methyl, then there would be symmetry. 1/2 of the molecule would be identical to the other. All 4 substituents on each double bond would be identical. See, 3 and 4 have 2 hydrogens, that's identical. 2 and 5 are hydrogens, that's identical. But the only difference is 1 and 6. If they were identical, then EZ would be identical to ZE. So 2E4Z would be identical to 2Z4E. And we would have only three different isomers. But in this case, because there is no symmetry, we have all four possible isomers. Also note how we represent isomers. E, or trans double bond, is represented in line drawing in such a way that substituents are on the opposite sides of double bonds. So you see, this is E and this is Z. This is 2E, 4E. And note Z. Substituents are on the same side of double bond. So this will be 2Z, 4E. This is 2E, 4Z. And note 2E, 4Z is different from 2Z, 4E. If they're identical, then there are three substituents. Sorry, three isomers. So when looking at number of isomers, that's usually where the trick is. Compare whether EZ is identical to ZE. And then we have ZZ, 2Z, 4Z. So in this case, there are four possible isomers. Okay, so this completes chapter 8. And again, I'm going to stop recording. And then once I stop recording, you can answer any questions if you had.